Hello. Today I'm going to go over a number of items in our reading queue. Hope you'll find these interesting, as we're not going to have our normal Saturday meeting this week, and hopefully we'll return next week with a full meeting. So the first thing I'd like to talk about is in the world of complex networks. And this paper in particular, a generative model for community types in directed networks. So this is where they're working with these hairball networks and they're trying to extract community types. This is a picture of a hairball network. As you can see, you have some structure, but a lot of it is just really kind of hard to understand. And so one of the things we try to do in complex networks when we build a very large topology, and this is a topology of the internet, is to break apart the topology into different communities or groups of nodes that share commonalities, that are either highly connected within themselves or some other criterion that we can define as a community. And so as you can imagine, this is intense computational tasks to find these communities, to find ones that are self-contained and robust. As you can imagine, you can find many different overlapping communities, but that's not necessarily helpful. And so in this paper, one of the things they talk about is how connectivity in the growth of a network results in being able to define different communities. So let's go to the abstract. So the abstract reads, large complex networks are often organized into groups or communities. And so you saw that big topology of the internet, and there are subgroups within that are groups or communities. We can use community finding algorithms to find those groups, and they usually have some significance within the network. It's the sort of the units of the greatest interaction locally. In this paper, we introduce and investigate a generative model of network evolution. So they're using a generative model. They're basically creating a network. They're generating it from the sort of the principles that they want to generate it from. And crucially, they're adding nodes to an existing structure and generating this sort of large topology, this hairball. So we look at network evolution. And this type of technique for generating these hairball networks reproduces all four pairwise community types that exist in directed networks. And so they go on to define these pairwise community types, which are essentially equivalent to structures that you see at the global scale or connectivity rules that govern the addition of nodes. So our four types are assortative, core periphery, disassortative, and what they call source basin type. And this is a newly introduced type. So the value of this paper is in introducing this source basin type. We fix the number of nodes and the community membership of each node, allowing node connectivity to change through rewiring mechanisms that depend on the community membership of the involved nodes. So what this means is that you have sort of a limited size, and you have this membership criterion. So when we add a node or we rewire a node, we change the edge in terms of where that node is connecting. We have this sort of criterion that is met. So for example, if I'm a node showing up into a network, I wire to some other node based on some criterion. It's not just blindly connecting. And this is where we get a lot of these assortative and disassortative types of pairwise community types. So this is basically, there's this idea that you can reinforce community membership by using community membership as a criterion. And they do this to sort of bootstrap this process and identify these types of communities. We determine the dependence of the community relationship on the model parameters using a mean field solution. So they use this mean field model to determine this dependence. It reveals that a difference in the swap probabilities of the two communities, and this is just where there's a probability of a node changing communities during rewiring, is a necessary condition to obtain a core periphery relationship, which is, of course, this relationship where you have a core of highly connected nodes and a periphery of less connected nodes. And so you see this core periphery relationship in different topologies where you have differences in connectivity. It's usually maybe the more popular nodes or the hubs that are core nodes, and then peripheral nodes that play a lesser role in the network. And that a difference in the average integrity in communities is a necessary condition for a source-basin relationship. So they'll talk about the source-basin relationship more specifically here. More generally, our analysis reveals multiple possible scenarios for the transition between the different structure types and sheds light on the mechanisms underlying the observation of the different types of communities and network data. So this kind of goes through the pairwise community structure. This is the math here. So the type of pairwise community structure for two communities, R and S, which are two communities, is determined by the density WRS on the edges between nodes in these communities, defined in this way. So you have your WRS, and then that equals within this stack, these conditions. If R does not equal S, then you have this rule. If R equals S, then you have this rule. And so this, they kind of go through this. But they also want to know something about some of these other methods. So they want to know something about assortative networks, core periphery networks, and disassortative networks. And so this shows the relationship between WRS and WSR, which is like the cross connectivity. So if you go in one direction between R and S versus in the other direction. And so they have these criterion for these four conditions. And so again, assortative connectivity is where you have this like assorting with like. Core periphery is where nodes that are rewiring are attracted to core nodes. Disassortative is where nodes will go outside of their existing community. And then source basin is this idea that there's a sort of gravity in connectivity, so it'll grow to the community of closest gravity. So it's kind of a combination of core periphery and assortative. And so this is an example here in figure 1 of sort of this type of connectivity. So again, we have these bidirectional connections where we have 0 and 1, and we can go from 0 to 1 or 1 to 0. And then we have these, so you have an outbound and an inbound connectivity. And so that's what these pairwise relationship looks like. But then you have assortative, core periphery, disassortative, and source basin. So assortative is where you have two communities and you have connections between the communities that are sort of highly selective. Core periphery is where you have a core of nodes and a periphery of nodes, and so they have this highly evolved, sort of highly there's this high degree of organization amongst them. Disassortative, of course, is where you have two communities, but they're not really interconnected very well. So they're classified as two groups, but they're connected with, between each other more than within each other. And then source basin is where you have the source, and then you have a basin here. So you have these this group that's highly connected, and this other group that's connected to that other group, but they're in this separate group. They're not really that well connected. So it's almost like a sort of disassortative connectivity, but also kind of like assortative connectivity in that you have one group that's highly integrated. So they provide this phase space. And so this is where we have, so in this case, we have core periphery. So we have the peripheral nodes in red, the core nodes in blue. You see that there's this core of highly connected nodes and this periphery of lesser connected nodes. You have source basin, of course, the source being these red nodes here. That serves roughly the role of periphery. and these basin nodes that are roughly the core, role of the core. You then have disassortative, where the red nodes and the blue nodes are not really any sort of, there's no organization between them. They just interconnect with one another. Core periphery, of course, is here again, and then assortative, where you have this like assorting with like. And so with this phase space, we have these two, sort of this bivariate space, where you have core periphery at high values of PA1. You have core periphery at high values of PA0. The disassortative connectivity for low values of PA0 and PA1. Assortative for high values of PA0 and PA1. And then source basin kind of taking up the rest of the phase space, which is, of course, probably one reason why they wanted to discover this new type of connectivity, because there was this blank part of the phase space. So that's the way they kind of think about this problem. And I think it's an interesting approach to this sort of, rewiring problem, or this connectivity problem, where you have new nodes that are coming into a network and then you decide where they're going to insert themselves. Or sometimes you have rewiring processes, say in the brain or in social networks, where you have to change your connectivity. And you change your connectivity sometimes based on the current activity of the network. So as the network is active and there are these active exchanges of information between nodes, they rewire in a way that's more amenable or more efficient. And so capturing this process of how this happens is important to understanding these communities. So now I wanted to get in a little bit into AI stuff, and we have some readings on. Okay, so now I wanted to get a little bit into artificial intelligence, and I have two readings on that. One is in this developmental AI area we've been working on, and the other one is something from Numenta that's really interesting. So the first thing is from the Los Angeles Review of Books. And this is a conversation between Alison Gopnik and Melanie Mitchell. Alison Gopnik is a developmental psychologist. Melanie Mitchell is an AI person. And they're talking about how to raise your artificial intelligence. So, there's this developmental AI theme that we're working on in the lab. So, one of the things that they're interested in, a lot of people are interested in developmental AI. And so, we have models like large language models. They basically extract patterns and data. And then the question is whether they really understand it enough to give a reasonable output, or whether they're reliable enough to rely on for any sort of casual use. So Alison Gopnik and Melanie Mitchell were skeptical of the assumption that we will be able to feed large language models enough text and become intelligent agents. And so, if you're taking a developmental perspective, you know that just training a model on data without any sort of structure or, any sort of aspect of development is probably not going to work. And so that's what they're discussing here. So, Alison Gopnik, of course, is interested in development, but Melanie Mitchell is also interested in a lot of things having to do with conceptual abstraction and analogy making, so more of the symbolic approach. So this is another issue with large language models, is there isn't the symbolic layer to large language models. So, it's another interesting take on this, is that they're kind of bringing these two perspectives together. Yes, what today's LLMs can achieve by consuming huge swaths of text is impressive, and has challenged some of our institutions about intelligence, and has challenged some of our intuitions about intelligence. Before we can attribute them to something like human intelligence, AI systems will need the ability to actively interact and engage with the world, creating their own mental models about how it works. So this is going in the direction of creating these mental models. So one of the questions here is, let's start with the tension at the heart of AI. We understand and talk about AI systems as if they are both mere tools and intelligent actors that might one day come alive. Alison has argued that the current popular AI systems, large language models, are neither intelligent nor dumb, that those are the wrong categories by which to understand them. Rather, we should think about them as cultural technologies, like the printing press or the internet. Why is a cultural technology a better framework for understanding large language models? And I think in the Slack, we've discussed the idea of a cultural technology. And so this is, this type of thing like the printing press or the internet, where you create this technological tool and people use the tool, and the imprint of the creators are sort of the thing that we get out of the technology. It's not the technology imposing itself upon the rest of us. And so I think that's a very important thing that the technologies themselves are rather passive. And as humans, we use those and we're able to, derive great works of, creativity out of them or something else. So Alison's response to this is a very common trope is to treat large language models as if they were intelligent agents, going out in the world and doing things. That's just a category error. A much better way of thinking about them is a technology that allows humans to access information from many other humans and use that information to make decisions. We have been doing this for as long as we've been human. Language itself could be thought of as a means to allow this. So we are writing so are writing in the internet. These are all ways we get information to other people. Similarly, LLMs get us a very effective way of accessing information from other humans. Rather than go out, explore the world, and draw conclusions as humans do, LLMs statistically summarize the information humans put on the web. And so Melanie Mitchell, of course, then also mentions that we use a lot of metaphors to talk about large language models. Things like autocomplete on steroids and stochastic parrots, or a blurry JPEG of the web, or cultural technology. So these are all metaphors that sort of speak to the sort of limitations of large language models, or the sort of the need to make them passive instead of active. Others use metaphors that have more to do with agency and understanding. I'm not sure we've come up with the right metaphor because in some sense, large language models are all these things. And maybe we have to say to what extent they are each of these things. There's such a big debate in the AI community about this, and it's interesting that such smart people can so violently disagree on how to think about these systems. So, because this is challenging our notions of what intelligence means, it becomes very contentious. Back in the 1970s, a lot of people were saying if a computer could play chess at a grandmaster level, that would require general human-like intelligence. Clearly, it did not. We thought the same thing about translation, which is, of course, translating to different languages. And, of course, people try to do that now, but this is not something that we've achieved since the 1970s. Now we're faced with systems that are conversationalists and are able to act like agents that understand conversation. Does that require human-like intelligence? It doesn't seem so, since we have these machines that can't seem to do things that we would say would be benchmarks of human intelligence, but can do other things that are quite complex. So maybe those things aren't at that level of human-like intelligence. And so to step back for a moment, it's a very interesting question. And we've talked about this in meetings in the past where we tried to define intelligence and talked about the definitions of intelligence. And it's very hard to have get a good grasp on what intelligence actually is. And so, we're thinking about how we sort of assign the term intelligence to things. Or, we assign human-like intelligence to things that may not be human-like intelligence. So Alison adds, there is an implicit intuitive model that everyday people, including very smart people in the tech world, have about how intelligence works. There's this mysterious substance called intelligence, and as you have more of it, you gain power and authority. So, this idea that intelligence is this thing that you have, it's something that's almost like a substance or a fluid, and then the more you have of it, the better, or the more authority you have, or the more power. But that's just not the picture coming out of cognitive science at all. Rather, there's this very wide array of different kinds of cognitive capacities many of which trade off against each other. So being really good at one thing actually makes you worse at something else. To echo Melanie, one of the really interesting things we're learning about large language models is that things like grammar, which we might have thought required an independent model building kind of intelligence, you can get from extracting statistical patterns and data. Large language models provide a test case for asking, what can you learn just from transmission, just from extracting information from the people around you? And so sometimes, intelligence isn't intelligence the way we think of it. It's this extracting information from data. So this next question is, what do you think are the limits to what large language models can achieve just by being trained on language alone? And so, they talk about this question. Alison says, if you look at, for instance, videos of the various best robots people are inventing, you'll notice that there's a little number in the corner that says 10x or 20x or something like that. And what that means is that the video has been sped up 20 times to make it look like the robot is doing something intelligent. If you were actually watching the robot in real life, it would just look like it was incredibly painfully slow and awkward and making mistakes all the time. This is representative of what's called Moravec's paradox. Things that looked as if they would be really, really hard for AI and require a lot of intelligence, like playing chess, turned out to be relatively easy. And things that look like any 2-year-old can do them, like picking up an object and putting it in a pot and stirring it, are actually really hard. Large language models have made that paradox more vivid. So this is, something that, again, we have this model of intelligence that may not be the best model to operate off of when we're thinking about artificial intelligence. But also we have this aspect of, that acquiring intelligence is actually not, a linear, straightforward path. That you have to make a lot of mistakes. And that, people think, well, if you make a lot of mistakes, you're not very smart. Well, that's not necessarily the case. It's more about exploration. We've talked about a lot of the stuff that people are doing with GoPro cameras and capturing images of the environment and training agents on those data. So this is all very much of the same, topic or the same problem. Is how do we sort of think about intelligence? How do we incorporate that into a machine? And it seems as if don't really have that first part down. How do we get intelligence into a machine, or how do we get information into a machine so that it actually expresses intelligence? But going back to the contrast between different kinds of intelligences, one type of intelligence is about what I call transmission, or how do I pass information to and extract information from another person. A different kind of intelligence is about truth. I am in the world, and the world is changing. And this is what they call a non-stationary environment. So how do I find the truth about something that we haven't seen before? Science is the most dramatic example of engaging in this activity, but even very young children are good at this. And large language models are, of course, not trained to do this. And so we talk about how they hallucinate, but hallucination isn't really the right word. To hallucinate, you mean that you would recognize the difference between truth and just a bunch of things that people have said. Large language models are not designed to make that distinction. Yeah, I think hallucination is a poor term for what large language models actually do, which is spit out terms sometimes that have nothing to do with the prompt or nothing to do with the topic that they're talking about. So, hallucination is if you think about humans hallucinate. Hallucinations aren't just, random stuff. It's, sometimes you have very specific hallucinations about, say, things that you know. So you might have a hallucination about big giant grapes in the desert and how you're bouncing from grape to grape along the landscape. And that's a hallucination that is based on a lot of, it's putting things together in this sort of way that's sort of believable, but it's not something that you would think is a real experience, if that makes sense. And this non-stationarity aspect is interesting because this is something we're exploring in our paper on the Everett regulator theorem and AI, and so that's something that's coming out from the lab soon. But this is, again, has to do with this idea of non-stationarity of the data that's coming into the system. So when the data is normally distributed, when it's in distribution, when it's stationary, that's a totally different situation than when the world and the data associated with it is non-normal, out of distribution, and non-stationary. And so this is a problem that is really interesting, I think, because it really affects the way that the AI acquires information and ultimately how it operates on that information. We might also have another opportunity to do a paper in terms of thinking about non-stationarity and developmental AI. And we haven't, that paper isn't as far along yet, that paper idea, but that's something that's maybe an opportunity for people to engage with. So, this interview goes on. There's a question about how large language models rely on statistical associations rather than concepts. And of course, this is the aspect of, symbolic AI versus non-symbolic AI, or neurosymbolic AI, which combines the two. And so, of course, Melanie Mitchell answers this question in the following way. A concept is a mental model of some aspect of the world that has some grounding in truth. You might have a concept of something like a unicorn. And while it is not true in the real physical world, it is actually true in some different kind of fictional world. I know it's fictional, but I still have a concept of it, and I can answer questions about it. I think these mental models of the way the world works, which involves things that cause other things, are concepts. And this is something I don't think large language models have, or maybe even can develop on the scale that humans do. And so again, Alison Gopnik makes the point that, mental models are different from statistical patterns. When you have a mental model, you also have an idea that you can go out and test whether the model is right or not. I can actively go out into the world, do an experiment, get the right kind of new data to decide whether I'm right or wrong. So when you have a set of concepts, you can take data, you can evaluate it, and you can go search for data that support that idea. And maybe that's a bad thing in some cases, but it's a different way of acquiring information than what you would have if you just kind of acquired information at random and incorporated it into what is essentially a very generic model, not necessarily a mental model with affordances and with specific concepts. And so, this kind of goes on for quite a while, so I don't want to get through the entire interview, but this is something we can follow up on where, they talk about a number of really interesting questions, but it's all in the same vein. So this is a really interesting interview. Now I want to move on to what Numenta is doing, and this is their 1,000 Brains project. So, of course, we know about Jeff Hawkins and Numenta and some of the efforts they've made to understand neocortical columns. And so, their whole basis of AI is on these neocortical columns, which are these multiple layers of brain tissue that are connected in a hierarchy, and it allows you to put those in parallel and do computations in a way fundamentally different than, say, like a deep learning network, where you have these generic units that are interconnected with hidden layers and all of that. So this is, Jeff Hawkins actually wrote this book, 1,000 Brains, Theory of Intelligence. And so 1,000 brains refer to these columns, putting these columns in parallel and actually being able to compute with them. And so Numenta has actually been working and building a community around their software. Their software is based on this principle, and they've been trying to, how do you take these insights about neocortex and apply them to artificial intelligence? So, they're not promising this sort of neurosymbolic revolution. They're promising this different type of processing. And the idea is that, the brain, to be successful at artificial intelligence, you need to model things more on the brain. and specifically the human neocortex or the mammalian neocortex. And you might agree or disagree with that, but that's the way they're pursuing this. And so to build the kind of efficient and robust intelligence that we know humans are capable of, we need to design a new type of artificial intelligence. And so now they're building this community. They're releasing this short technical document describing the core principles of the platform. So they have very good documentation of their approach. This is something that their community really has down. They've been working on these technical documents for years, and they're putting out sort of the core principles of the platform. They have some code on GitHub, so this is something that can be pursued pretty easily. And so, this kind of gives you some information about how you can use Numenta. You can do things like sensory motor learning, work with reference frames, so you can actually put in spatial reference frames or conceptual reference frames. I guess in this case, they're showing an observer, in looking at some object and having these spatial points of reference. Of course, you have sensory motor integration here, sensory motor feedback from objects. Then you have modularity, which is, of course, where you have these modules. Maybe if you have a robot where you have these columns, you can have some columns devoted to sensory input, some columns devoted to learning inputs and learning processing and other things. So you can have, different components of your massively parallel system. And so, like in human neocortex, you have some areas devoted to visual inputs, you have some areas devoted to visual processing, some devoted to sensory motor processing, some devoted to higher level concepts and the like. And so this is sort of the other principle of the 1,000 brains, which is that you can have these modules, but everything is in parallel. And so this is a really powerful, potentially powerful way of doing this. So they have an SDK that you can use. This allows you to develop more easily, especially some of these alternative architectures. So once you get into the world of Numenta and you learn the way it's supposed to work, and you learn the vocabulary and the tools that they have, then you can play around with these kind of approaches where you have multimodal modules, a wider set of modules. You have deep and wide networks where you can have things that are sort of hierarchical and things that are distributed. So there are a lot of sort of architectural variants that you can play with. And depending on the problem, some of these might be quite useful, some of them less useful. And so this is their, kind of update on their system and their community. So if you're interested in participating, we have some interest in this in the lab, some interest in bio-inspired stuff. So, please let me know if you're thinking about something like this. All right, our next topic is on emergence. And there have been a couple of good articles on emergence that have come out recently, and I wanted to go over those and talk about their significance. So this is an article from Quantum Magazine, and this is on the new math of how large-scale order emerges. So this is based on the idea that, we know about emergence, and we've known about emergence for a long time. And the puzzle of emergence asks how regularities emerge on macro scales out of uncountable constituent parts. So when you have a flow like this, and this is a flow on the surface of Jupiter, this is Jupiter's great spot. And the idea is that you have all these components that come together to form these patterns. And so the thing is that the constituent parts don't have a plan for this structure. They don't have the ability to sort of collectively coordinate themselves to build these patterns. So how do you get to this? And the answer, of course, is emergence. So things emerge out of just interactions. There's no plan, but those interactions determine the sort of the scope and scale of this pattern. And so this is something, of course, that diverges from what we think of as artificial intelligence, because you just need agents at the local level making interactions. Sometimes the interactions are regular, sometimes they're stochastic, but they can produce these larger scale patterns. And it doesn't require sort of an intelligence, it just requires interactions locally. So there's some maybe intelligence in the agents if you were building an AI system. But sometimes they can be, chemicals, they can be, particles in a flow, whatever. And so those don't really have intelligence. And so emergence is conveniently, it gives us the ability to sort of understand those sorts of things. But there hasn't really been a very rigorous mathematical description of emergence. And one of the reasons why, of course, is because it's hard to describe a process that's essentially stochastic. So you have these things locally that are happening and they result in these patterns. How do you describe that in mathematical terms? How do you use a symbolic system to describe that? And that's really the problem that they're getting at here. So this article is by Philip Ball. This talks about this image is, of course, Jupiter's great red spot, and this is a pattern that's been sort of emerging over hundreds of years. And so you can have emergent patterns at different scales, at different time scales and different spatial scales. And so, we see emergent phenomena everywhere in the world, but it's hard to know kind of, if all of these different types of patterns have the same set of principles behind them or if they have different principles. And so, it's hard to know, like we can kind of explain why emergence happens, but we don't have a really strongly predictive model of how emergence happens. And so Jim Crutchfield, who's at Santa Fe, says confusion is reigned, it's just a muddle. We don't necessarily know, if something is truly emergent, whether any one pattern follows the same rules as any other pattern, and so forth. Neil Seth, who of course is a neuroscientist, says philosophers have long argued about emergence and going around in circles. The problem, according to Seth, is that we haven't had the right tools, not only the tools for analysis, but the tools for thinking. Having measures and theories of emergence would not only be something we can throw at data, but would also be tools that can help us think about systems in a richer way. And so, people have been working on this problem, and in recent years, people have kind of come up with some novel ideas about this. So Fernando Rosas, who's a complex systems scientist at Sussex, along with Neil Seth, they worked on this framework for understanding how emergence rises. And so this framework is in this arXiv paper, and this is called Software in the Natural World, a computational approach to hierarchical emergence. And so this is, of course, the paper here. There are some other famous authors on it. And the abstract reads, understanding the functional architecture of complex systems is crucial to illuminate their inner workings and effectively or enable effective methods for their prediction and control. Recent advances have introduced tools to characterize emergent macroscopic levels. However, while these approaches are successful in identifying when emergence takes place, so we can identify an emergent pattern when it's happened, and this is largely from static information, or sometimes we can see something emerge if it's a chemical form of emergence. If you see a pattern in a coffee cup or in a chemical reaction or on the surface of a planet, or in a puddle of water, you can watch it kind of take shape, or you can watch an ant colony form. It patterns of its behavior, and you can see this, but it's really hard to know how it does this. And so one of the problems, of course, is that it does it in different ways every time it does it. So there's this idea of initial conditions. So if the initial condition is different, these structures are built in different ways, and they can follow different types of interactions. You can't reverse engineer an emergent structure and get an exact solution to it. You just have like a number of ways that it can emerge, and that's as much as we know. So people are limited in the extent that they can determine how an emergent pattern happens or comes to be. Here we address this limitation by developing a computational approach to emergence, which characterizes macroscopic processes in terms of their computational capabilities. Concretely, we articulate a view of emergence based on how software works, which is rooted on a mathematical formalism that articulates how macroscopic processes can express self-contained informational, interventional, and computational properties. This framework establishes a hierarchy of nested, self-contained processes that determines what computations take place at what level, and which in turn delineates the functional architecture of a complex system. This approach is illustrated on paradigmatic models from the statistical physics and computational neuroscience literature, which are shown to exhibit macroscopic processes that are akin to software in human engineered systems. So they're making this analogy between software and the structure of software and things that are happening in statistical physics and computational neuroscience. Overall, this framework enables a deeper understanding of the multi-level structure of complex systems, revealing specific ways in which they can be efficiently simulated, predicted, and controlled. And so why don't we look at the paper to see if there are any good figures, because that's often a good way to sort of summarize what's going on. So the first figure is illustration of causal states. This is interesting from, the perspective of having this metaphor of a software architecture and having it, be generative and being able to produce these emergent states. This paragraph here is interesting. Arguments can be made based on evolutionary and thermodynamic considerations for why and to what degree biological systems may display software-like macroscopic levels that are causally closed. So this is interesting because we've been reading some work in, I think it was this cybernetics reading group, on how emergence is really, or biological emergence is really not something that's programmatic. It's not something that can be captured using an algorithm. And in this paper, they seem to be making the opposite case. You can have causally closed systems that are, you could see them perhaps in biology, that are basically programmatic, or I guess you could say algorithmic, although we can play around with this idea. And so, software-like, I think, being the term of art, that would be the point of contention. So, do biological systems display the software-like sort of organization? And if so, then can we use that to make predictions about emergence? Because if we have biological emergence, and it's structured in the same way a program or a generative program might be structured, and a generative program can produce an emergent output, then maybe the biological system can as well. Living organisms perform actions, for example, interventions over their environment and themselves, in order to guarantee their survival. However, some interventions are more feasible to implement than others. So while it is almost impossible to intervene on the momentum of a particular molecule in a glass of water, so you have this thing that's happening at the macroscopic scale, it's hard to intervene upon that, which I guess means you can't really, you can't make an intervention, so there's this causal consequence to that. It is much easier to increase its mean temperature together with all the molecules in the glass. So you can basically take a glass of water, heat it up, and ensure that all the molecules will heat. And of course, that has the emergent phenomena of creating maybe a phase transition to a gas, or evaporation of water, or boiling water, so you get right up to the phase transition. But it's harder to say. It's easier to heat the glass with everything, all the molecules being heated, than to intervene at the level of specific components of that emergent system and modify them accordingly. And of course, sometimes we don't need to do that because, heating a glass of water is a mean field thing. In other words, the molecules all sort of behave in the same way and they have a similar response. And so we don't really need to worry about making those interventions on the individual scale, at the microscopic scale. we can observe a macroscopic effect by having this sort of macroscopic intervention. Causally closed systems are those for which macroscopic interventions are efficacious in controlling their macroscopic scale. So this is where this is the causally closed system that we just talked about with the glass of water. Hence, one can say that systems are as if running software to the extent that they are controllable at a particular scale at a reasonable thermodynamic cost. So this is an interesting statement. So wherever you can control a system, if you can control the system, say at the macroscopic scale, then there's it's easy to predict what's going to happen macroscopically. If you can intervene at the microscopic scale to affect the macroscopic state, and what they mean by reasonable thermodynamic cost means that you're not trying to you're doing something that was within sort of the bounds of the thermodynamics of the system, or you're doing something that is not extremely costly. And this is the same kind of analogy we have with algorithms. We don't run a brute force search on things and wait around 150,000 years for an answer. We have to create these heuristics. And so there are a lot of analogies between computer science and natural systems that are really interesting here. And so, we're talking about sort of issuing commands and processing data and things like that, but we're doing this in a way that interacts with physical systems and biological systems. Building on similar arguments, causal closure has often been regarded by theoretical biologists as a necessary, albeit not sufficient, condition for the subsistence of living systems. So we've talked about causal closure before as well, and this is, of course, tying in with that literature. So they draw heavily from computational mechanics, which is a framework for the study of stochastic dynamical processes from a computational perspective. And so it studies patterns and statistical regularities observed in time series data and asks quantitative questions such as how much historical information does the system store, where is that information stored, and how is it processed to generate future behavior. So this is something that, if you're studying a system where you have this cumulative output, so in other words, you make interventions at the microscopic level, and an accumulation of those have an effect at the macroscopic scale, but this doesn't happen for a while, then, it's kind of hard to understand that in terms of single interventions. You have to take the sort of computational mechanics approach to understanding. And I guess what they mean by computational mechanics is that you're looking at the statistics. It's sort of like statistical mechanics, but you have this computational cast over it. So you can create these types of machines that they're talking about here. Epsilon machines. These are optimal, complete, and minimal representations of a computational engine that can generate the patterns observed in data. So you have these representational structures of the statistical mechanics of this natural system. Such representations can be built by grouping past trajectories according to their forecasted futures into so-called causal states. More precisely, the causal states of a time series are the equivalence classes of past trajectories that are established by the following equivalence relationship shown here. And so this is where the causal states are given by a mapping epsilon, which coarse grains past trajectories x at t, thereby generating a new time series of causal states, this set E. Formally, the epsilon machine of x is defined as a pair where epsilon is the above mapping to causal states, and this t term is a collection of transition probabilities in this form here. So this gets into their epsilon machines where, they kind of show mechanisms and observations versus inputs and states in this way. So the first one is this causal phase. And this is a view of epsilon machines as the effective mechanism driving the system, acting behind the scenes to generate observable data. And that's an A1 here, where you have sort of this, almost looks like a reservoir computer producing some patterned output. Technically, this corresponds to interpreting it as a hidden Markov process, or dynamics that take place in variables e sub t on a weight and state space, while generating the observable data x sub t. Then you have this computational phase, which is B. This is an alternative view of epsilon machines as discrete automata. So in this state machine, where the data corresponds to inputs given by a user driving the system between different states. Technically, this corresponds to seeing it as a discrete automata with states e sub k, whose deterministic transitions are governed by the input data x sub I. And so this is where you have these two different ways of doing this. And causal states correspond to a kind of information bottleneck. So, you have to engage in a number of activities like coarse graining of past trajectories so that you can have some sort of predictive power. The causal states also have Markov dynamics, and by Markovanizing the process, this forces the effective states of the process to become explicit. So this looks like some of the stuff that we're arguing in terms of the Evergood regulator theorem and how that can be applied to this outer distribution data, this sort of non-stationary data. And so this is a really interesting approach. It's a little tough to understand, I think, for someone who's has a casual interest in analyzing an emergence system, but I think it's a really interesting approach. Okay, now I'd like to move on to talking about spreadsheets and using spreadsheets to do things like build a transformer or a large language model. And so we talked about spreadsheets being used to build something like an urban simulation like SimCity. And so we talked about how spreadsheets can be used to sort of manage those simulations and build the sort of the nuts and bolts of the simulations. And, I had a question about that was basically like, yeah, it's obvious that you can use spreadsheets. And of course, wasn't kind of the point of what I was trying to get across there. The point of what I was trying to get across is that spreadsheets represent a certain computational tool. And that it's sometimes viewed as sort of in a dismissive way, that it's a very simplistic tool that doesn't really have a lot of use in sophisticated computation. But we can actually use spreadsheets as a way to sort of represent very difficult problems, things that might take a lot of computation, but we can sort of get an intuitive understanding of it using a spreadsheet. And so that's where these readings come in. So the first thing is this term spreadsheet is all you need, which of course plays on the classic paper title, attention is all you need. And so unfortunately, attention isn't all you needed, as we found out later, but it's a good title. But this is Dabo Chen on GitHub, and this is the Spreadsheet is all you need repository. And this is a nano GPT pipeline packed in a spreadsheet. So this allows us to build a very small version of a large language model. And it's packed in the spreadsheet, which is here, Nano GPT Excel XLS. And so I'm not going to open it up because I don't have the program for it available, but we can actually, open this up, clone the repository, open it up and see what it looks like. But this is basically the README here. This is where you can build this Nano GPT pipeline. It's pretty fun to play with, especially when you're trying to figure out what exactly is going on inside of a transformer. So there's this interpretability value to it. This helped me visualize the entire structure and data flow. All the mechanisms, calculations, and matrices inside are fully active and configurable. So basically what he's done is created these tables in a spreadsheet, and it kind of walks through some of these transformations that you need to make. A lot of matrix algebra that you can do in a spreadsheet. But it makes it kind of salient to people and understandable. You can view the data as a table or as a matrix instead of just kind of like thinking about the code and what it's going to look like. You can actually have that in front of your face, and it makes it easier to understand, I think. And this is, I think, a missing piece of interpretability, is this aspect of seeing the data being processed, or seeing what the data should look like in front of your face, not necessarily in a plot, but in the sort of raw, matrix of numbers and how it changes. And then you understand, okay, this is what's happening inside the transformer. This is what's happening inside the model. This is how we're getting our answer. And so while reading about large language models, I realized that the internal mechanisms of a transformer are basically a range of matrix calculations being connected in a certain order. So basically, you're taking these matrix calculations, you're putting them in an order. And you can see that in the spreadsheet. Everything is sort of visualized for you. And in a way that isn't like just kind of like a diagram, you can actually see the data change, and you can actually trace things back, which is crucial, I think, to understanding how the large language model got its answer, arrived at its answer. I started to wonder if the whole process can be represented in a spreadsheet, since all the calculations are fairly simple. I'm a visual thinker. I couldn't think of a better way to do it. And so this is kind of going on through, this is not Python, this is a spreadsheet. And the spreadsheet apparently is all you need. And this is, of course, is the self-attention mechanism, the core of the transformer. And again, you open up the spreadsheet, and this is what it shows. It shows these tables that transform to other things, and it's easy to see. What components will you see? So it contains all the transformer components, including an embedding, a layer norm, self-attention, projection, a maximum likelihood probability, softmax, and logits. And this is based on Andre Karpathy's NanoGPT structure, which is an 85,000 parameter model. So this is something that is one of these very small GPTs. It is very clearly a very small size, but is both complex enough for me to understand how it works, but also not too big to crash my computer, which of course we talked about with the Raspberry Pi implementations of a large language model. And the small models are actually very important, I think, for understanding how the model works. It's the old adage, you have to learn to run before you can fly. So I think that's a good sort of use case for this. But also, you can do things and just kind of understand how to train something, how, something is sort of implementable, if something is implementable or not. And you can, of course, train it on very small data sets if you want. So you can get very small data sets and very specialized information. And so, yeah, there's a lot more in this README, including some YouTube videos on Let's Build GPT, the NanoGPT project, and 3D visualizations of transformers. This is particularly interesting. There are different types of visualizations people have used of transformers. This is an interesting visualization. This actually is a visualization of NanoGPT, not in a spreadsheet, but it's in this sort of three-dimensional diagram here. Oops. And so if we zoom in, and actually they have it for GPT-3, GPT-2, both extra large and small. And so you can see these different components here where they have the different matrices. And you can zoom in on the matrices. So, we're zooming in on the different weight matrices, the vectors, softmax vectors, softmax matrices, the projection weights, maximum likelihood weights, activation, and so forth. So we have all these different components that we can zoom through this 3D model. I don't know what they're modeling this in, but it's really interesting. And so now we have this article by Kevin Lubick. This is his approach to this, building an ML transformer in a spreadsheet. So this is actually the same one. Attention is all you need. Introduce transformer models, which have been widely effective in solving various machine learning problems. And so he actually did his own version of this, where he created a transformer in a spreadsheet and made a video walking through it. So this is a YouTube video that talks about creating a transformer in a spreadsheet. At a high level, transformers are effective because they convert the data in a way that can make it easier to find patterns. They build on ideas from convolutional neural networks and recurrent neural networks. And this has to do, these are analogies to focus and memory. They use these terms from cognitive science and they kind of bring them to neural networks. So the convolutional neural network is focusing, and the recurrent neural network is the memory component. And this is combined into what they call self-attention. Okay. So implementing the transformer really helped me understand all the components. So another point for that. I'm especially proud of my metaphor of scoring points for explaining self-attention. These are some other resources on the attention mechanism in transformers. So yeah, it gives his own take on using spreadsheets to build large language model components, particularly transformers. So our final feature of today is to talk about theory and theory building. And we have 2 articles that have popped up in our Slack channels, so I'll go through those. The first one is this article by Grace Lindsay, David Barak, Sian O'Donnell, Stephanie Palmer. And this is a breakout room. I guess it's a perspective on a breakout room on something called the Transmitter, which I think is a neuroscience blog. And this is, must a theory be falsifiable to contribute to good science? And so this is sort of from the perspective of neuroscience, and they're talking about theory being falsifiable, or must it be falsifiable? And so in neuroscience, they have their own approach. In some sciences, falsifiability is important. In other sciences, it's less important. So keep that in mind. Falsifiability is considered by some to be the cornerstone of any scientifically sound theory. Indeed, certain schools of thought within the philosophy of science label theories that are not falsifiable as pseudoscience. But is the falsifiability or testability of a theory actually crucial for good science? Or can a non-testable theory still help drive progress? So a theory that you can't say is, an idea that you can't falsify, at least in principle, because sometimes things actually are non-falsifiable. And those are the stronger hypotheses or theories. If they're not falsifiable from the start, then they can't really be scrutinized. So that's why they're called pseudoscience. But again, like I said, in some sciences, in some forms of science, we can easily build falsifiable theories, falsifiable hypotheses, and others we can't. It's not easy to do. So this is another, this is a case where the philosophy of science gets ahead of the actual practice of science. And this is something that you have to keep in mind when you read philosophy of science, is that it's an idealization, and that it's not necessarily something that people think a lot about when they're actually doing science. But nevertheless, it's always important to keep it in mind, at least in terms of, where are we going? Because people tend to go in many different directions, and sometimes they run into problems with their ability to sort of separate the wheat from the chaff, let's just say. Neuroscience is a relatively young scientific endeavor, so we may benefit from more unconstrained exploration of ideas and theories. Making room for non-testable theories may help expand the space of ideas in neuroscience and provide footholds to grapple with increasingly large and complex data sets. Also, given that non-testable theories are already pepper the field of neuroscience, it is important to explore the role they are playing and how well suited they are for it. So, neuroscience has a lot of non-testable theories. And part of that is because we haven't traditionally had the tools to address those problems or theories. But also because we have a lot of sort of ideas that are very sort of out there in terms of how to test them. So we'll come up with the example of consciousness. And so consciousness is notorious for having non-testable theories. And so, do we really want to sort of have non-testable theories? No, but sometimes we have to. And it's just really kind of hard to get a handle on those non-testable theories. We can state something, we think something is true, and we say, how do we test it? And we say, well, if we had a way to measure the brain in real time over 30 years, we could do this. And of course, we don't have that technique. So it's a moot point. It's theoretically testable, but we don't have the ability to test it. There have been a lot of things, though, where the technology has caught up with the testability of the idea or the theory. I would also argue that neuroscience, even though it has a lot of quote-unquote theories, it's actually very devoid of theory. And that seems like a tautology, but it's not, because it isn't driven by theory. It's driven a lot by data and isolated questions. And then the theories that do exist are somewhat non-testable. So there's really a gap between like things that are just kind of things people assert that you can't test, and then things that actually are drawn directly from like data and investigation. So, we don't have like a theoretical neuroscience the way we have a theoretical physics. But the theoretical physics also has this problem in some cases where you can't test things. But in any case, that's where we are with theory building. So this is part of a week-long conversation with 3 researchers. Grace Lindsay, of course, is the moderator, so she's asking these 3 researchers, or doing a back and forth with them over Slack to try to define what qualifies as non-testable and what traits such theories tend to have. So, to say if something is non-testable, it can be like derogatory, but it also has certain properties. So what does it mean to be non-testable? And this is something that, we want to be able to sort of get our head around in terms of maybe what's clearly pseudoscience, and maybe what's just beyond the scope of our technological capabilities to measure, but maybe things that are actually testable. So maybe there are things in ideas that we can test, and sometimes it isn't obvious how to test something. And this is one thing when you're building, hypotheses or theories. You ask a question, you kind of construct a hypothesis, maybe you build a theory, and you say, okay, how could this be tested? And you have no idea. But sometimes you have to kind of think through how to test it, how to implement it. And it's not unlike in technology where you have to think out a pipeline to say, okay, we're going to build this thing. How do we do it? What are the components? What is the sort of the workflow that we need to follow? And it isn't exactly like that, but it has some similarities. So this is an important point, that you have to kind of think about if something is non-testable, maybe something is testable. Maybe something's clearly never able to be tested because it's just something that you're asserting, or it's something you can't observe. But maybe something is, if you could build the right measurement device, you could actually test these things. So a lot of the data we're getting from next-gen sequencing, a lot of the data we're getting from, smaller probes that we can put in the brain, or we can get things at higher spatial resolution now as opposed to like 50 years ago. We can then, maybe test some of the ideas that have been floating around the literature for that long. We describe specific examples from neuroscience with an emphasis on normative approaches. We also discuss challenges in accessing the quality of non-testable theories and the role they play in inspiring testable predictions. So sometimes we have non-testable theories that are sort of like out there because they guide us, not because they're predictions or they're highly predictive. So, we have ideas about things that are sort of normative, and then they lead to testable predictions because people build off of that. So it's just like an idea that someone throws out off the brain. Sometimes they're bad ideas like that. Sometimes they're good ideas. Like a bad idea would be the example of the triune brain, where there's a lizard brain and then there's a more evolved brain, and this is all kind of pseudoscientific, but the idea that it's normative, that it kind of structures the way we think about the brain, and then of course you might be able to build things that would test that prediction. That's what we're talking about here. By the end, we reconsider referring to these ideas as theories at all, opting for frameworks instead. So there's a lot of back and forth about what a theory is. We could spend many, many years having a conversation about actually what a theory is, believe it or not. And so in neuroscience, I think there's somewhat of an aversion to clear thinking about theory, at least in my opinion. And even just using the name theory is kind of a problem. People will use framework because so much stuff is driven by data and not like, other types of ideas. Although, when we get into the world of AI too, like I said about AI, in AI, they don't really have a really good handle on what intelligence is. But then they build on that scaffold of a really loose, poorly defined idea, and they say, oh, all of a sudden machines have intelligence. Well, sometimes we need frameworks to undergird what we're doing. So if we had a framework for intelligence and we're building an AI, we know kind of how we define intelligence, and then you can debate whether that's a good idea of how to define that, and then you build upon that to give yourself these, you can actually have testable theories and testable hypotheses based off of the framework. So, this is an interesting exchange here. They have this exchange kind of published. So this is a Slack discussion. And it kind of goes through some interesting things here. Here's a quote from Stephanie Palmer. In neuroscience, we have a lot of ideas, but fewer theories. Is anything that's not testable simply not a theory? So, there are all these sort of opinions on what theories are, what's testable, all this stuff. C.N. O'Donnell says, I have tried to interrogate ChatGPT for examples of a theory, but 90% of its suggestions are related to consciousness. So again, like I said, consciousness is sort of like a land of non-testable theories, or worse. Assuming we are steering clear of that topic, partially because IIT has already been debunked as pseudoscience by Grace Lindsay et al. They wrote this paper on this topic. So not to get too controversial, but that's what that's about. Then the only potential interesting examples I could get of it were, and so this is the list of theories in neuroscience that ChatGPT has generated. Cryptomnesia and hidden memories, which is the theory that all experiences are stored as memories in the brain, even if we cannot consciously access them, and they fall into a gray area. The extended mind theory, where the mind extends beyond the brain and body to include the external environment. Specific genetic determinants of complex behavior, the idea that complex human behaviors such as propensity for certain careers, specific personality traits, or detailed preferences are directly and solely determined by specific genes. That's difficult to falsify. And then neuroplasticity limits. Well, it's established that the brain has a significant degree of neuroplasticity, or the ability to reorganize itself. The precise limits of this plasticity are hard to define and test. So these are all things that are sort of theories in neuroscience, and they're all very hard to falsify or to test or that sort of thing. So this is interesting that, we have this this set of things that were generated by ChatGPT, and it's really just a summary of the literature. And this other point he makes also, since I recently ran a workshop on brain learning rules, I was thinking about Blake Richards and Conrad Cording's proposal that the brain must be doing gradient descent during learning. It's an appealing idea, but hard for me to see how to test. So this point here brings up something interesting, and that is that, sometimes we have theories, but sometimes those theories underlie or underlain by this sort of analogy building. And this is, I think, important for like neuroscience, because a lot of like theoretical neuroscience is, some, at least in large part, is based on like analogies with other things. Since, we don't have a very deep history of knowing what the brain is even doing, there have been a lot of analogies for intelligence or for what the brain does. I guess in gradient descent during learning, the brain is apparently optimizing things during learning. And so that's where the gradient descent analogy comes in. But, what does that mean? Is that the only thing that happens during learning? What is the brain doing during learning? It's obviously doing some sort of optimization, or it's doing some sort of like, well, we know that, like, for example, in machine learning, there's gradient descent, and that leads to greater learning. So the brain must be doing a similar thing. But if we look at what's actually happening during learning, there are a lot of things happening. There's acquisition, there's optimization, there's um, a loss function, I guess you could say. There are things going on at the molecular scale. There are things going on at the anatomical scale, and so on and so forth. So, it's really hard to kind of make a statement that sort of has the assumption of this analogy, and then build some sort of testable hypothesis off of that. And these other points, they have similar problems with them. Another aspect of this that's interesting is that, neuroscience kind of comes out of psychology, and psychology has, a history of having these sort of analogies for thought. And so, this is kind of an interesting point. Some of these analogies don't have anything to do with the brain, and they were just kind of pulled into neuroscience. That's another point. So this kind of goes through this conversation. Grace Lindsay says, I want to know, if we have two non-testable theories, A and B, how do we decide a priori which is more likely to inspire those experiments that will lead to a good testable theory? So this is, again, because we can't test things, we have rival theories. How do we know which one is better at maybe inspiring experiments, or actually something that is, has some testable aspect to it? And so this is a really good conversation. Again, this is something that we can go through maybe more in more depth later if people are interested. But this is something that could be debated for years, and probably there would be no good answer coming out of it. So our final paper or article for today is from the Four Gravitons blog, and this is a conversation between Yann LeCun and Elon Musk. I say conversation in a very loose sense, but the topic is about, does science require publication? And so this is about, this idea that, what qualifies as science? So obviously we know, we've talked about theory building and hypothesis testing and those sorts of things, and it makes maybe your science more or less rigorous. But, sometimes it's about letting the world know what you're doing. So if you do an experiment, or if you even do find that like some idea from neuroscience can be tested and falsified or whatever, if you don't let people know about it, it's not really science, because you just have it in your own head, and you need to get it out into the world so that other people know that at least you tried something and it maybe didn't work, or it did work, and you need to let people know about that. So the publication aspect is important. Now, I put a caveat on this, in that there's this separate conversation in the open science community about whether we actually need journals. And I don't think we need journals necessarily. You can publish your work in various ways. You can publish them as documentation, or in terms of lab notes, or you can publish them in preprint form. And, so publication can be very flexible. But I think the idea stands. What Yann LeCun says in the first part of this thread is that if it's not published, it's definitely not science, because if you don't put it out into the world, if you just keep it in your own head, it doesn't mean anything. It has to be a social activity. It has to be out into the world so people can read about it, people can understand what you did as well. So it's about description, it's about letting people know, it's about communication, and it's about sort of replication, allowing people to replicate it properly. So you don't want to just put it out as a series of tweets. You want to have full details of how something was done, how something can be replicated. So this little thread, he's responding to Elon Musk, who Jan LeCun says, well, if it's not published, it's definitely not science. Elon Musk replies, that is one of the dumbest things anyone has ever said, which I don't understand why that would be dumb. But and then Jan LeCun follows up, to qualify as science, a piece of research must be correct and reproducible. To be correct and reproducible, it must be described in sufficient detail. To be published or to receive a seal of approval, the publication must be checked for correctness by reviewers. To be reproduced, the publication must be widely available to the community and sufficiently interesting. So all these points are kind of, they kind of conform to a certain model of science. I don't think all of these things are necessarily absolutely required. There are different ways we can do this. But I think, things have to be sort of written. They have to be, published, put out into the public eye. And yeah, you need some oversight. So, I don't know about seal of approval. I mean, obviously, there are a lot of people publishing things that are there are papers that get retracted. You have people putting things out in the world that are, anti-vaxxer or, pseudoscience. And so we want to be able to sort those out and say those are bad and this is good. And so there has to be some sort of value judgment there. But I think the idea of being able to have a publication that people can refer back to that standardizes things, that tells people in the world what you found, how you did something, that's a very important part of science, that social aspect. If you do research and don't publish it, it's not science. Without peer review and reproducibility, chances are your methodology was flawed and you fooled yourself into thinking you did something great. No one will ever hear about your work. No one will ever pick it up and build on top of it. No one will build new technology or products with it. Your work will have been in vain. You'll die bitter and forgotten. I think that's a little over the top. But the point here is that, there's this aspect of, doing science and how we do science as a sort of a methodology. And sometimes that can get sort of bogged down in this idea of a cargo cult, right? You just you check boxes off to get things done. And that's the way some people think about science. There are other aspects of science too. There is a creative aspect. There is, of course, the idea of reproducibility and making your science kind of build upon itself. So if I publish a paper and it addresses this problem, can I build another paper from that? Or can I follow up that paper with another paper that kind of explores the topic? And so, there's this idea that a paper is sort of a minimal publishable unit. In other words, it might be a single experiment. It might be a set of experiments talking about, with a certain scope, talking about a certain topic. And so, what constitutes a publication is, you can question what constitutes a publication, but basically it's a unit of publishable work, maybe a minimal unit of work. And there's usually a series of those. So in the lab here, we usually publish things, we kind of follow up on a paper with another paper, and it addresses a different question. But in any case, I think this is an interesting conversation about what publications are, what they kind of accomplish, and so forth. I don't think it's a very complete discussion because, of course, there are these other aspects that are not talked about here. This was just basically built off of this sort of rift between people on X. So, I just thought it might be interesting to go over, to understand a little bit about how people think about doing science in practice. So that's all for today. Thank you for paying attention, and see you next week.